All right, good morning. Welcome to lecture number 7 of the course. Today we're going to talk about regression. And what we're going to do is take the previous lecture in which we saw the linear model from a mathematical perspective, and we're going to start making certain assumptions, plugging some distributions and some other assumptions, and we're going to start talking about the linear model from a statistical point of view. And this will lead us to the whole lecture on regression. As you saw, I was late this morning for the Q&A. I'm sorry, I had to do it from home, and a few things happened. But anyway, just FYI, if, as I said during the first lecture, I think it was, if you have any question about anything, you are free to ask in any of the Q&As. So even though they are they are named after one specific lecture, you're free to ask about anything we have seen so far. So don't worry if you have questions about models, you can ask next Monday. So let's talk about regression. And as usual, within the scope of the course, we're still covering these two parts. We're going to talk about building models, specifically linear models, and learning from those models. So in the past lecture, what we saw is the simple and the multiple linear model, which have a form like this one here. So there is a response variable, which is numerical, the y, and then we have the global intercept, and then from 1 to p features or independent variables, and for each of those we have a coefficient in the model. We also talked about dummy variables, which are these binary variables that we use to encode categorical predictors in the model. So essentially we have one variable for each of the levels of the categorical variable, and then each of those has an associated coefficient that can be seen as a deviation from the intercept. We also talked about interaction effects, in which we can model, for example, here the effect of both TV and radio together, and their effect on the response y. And what we saw is that they are, in this case, that they're both numerical, they're kind of reinforcing each other. So the TV, for example, has a main effect here, and then an interaction effect here, depending on the value of the radio. We also saw interaction effects between categorical and numerical variables, and essentially what that meant is that we can have multiple slopes and multiple intercepts, one for each of the levels of the categorical variable. So for example, over here, we had the example of people being insured or not. So this would be the deviation from the baseline for the group of insured people. Here we have the, the slope for the age, which is a numerical variable. And then here we have a deviation from that slope. So this is the one giving us the two different slopes. This is the one giving us the two different intercepts. And finally, we talked a little bit about transformations and how things like this are still a linear model. Because again, the important part is that the terms of the model, so this is one term, two terms, and 3 terms, 4 terms, they are all linearly related. And each of them has a coefficient. So this is still a linear model. And so today we're going to talk about the variability in the linear model and what is the main source of variability that is due to the training set. We're going to talk about quantifying this variability in terms of standard errors, intervals, hypotheses, etc. We're going to talk about one of the most likely uses you're going to find about the linear model, which is the case in which we want to compare means in the response across different groups. And then a little bit about model selection, and finally logistic regression. So let's see. Let's talk about variability in the linear model. And I'm going to refer again to this example we had in the previous lecture. Imagine that in reality, this is some phenomena that we're interested in studying. So we see that the response is a function of two variables, x1 and x2. x1 is numerical, and in fact, we see that there is a quadratic relationship between y and x1. And we have x2, which is categorical, and they're basically two groups, A or B. And now here in the plot, we see exactly what reality looks like for both groups A and B. They're just different in terms of the intercept. So let's say we make a choice about the class of models that we are going to assume. And again, we're going to assume that the response is affected only by x1 in a linear way, and we don't know anything about x2. We do it, let's say we sample some data or we collect some data. These are the points in the scatter plot. We sampled in particular 30 points. This black line here is the regression line, and these are the coefficients. And again, this is the estimate for beta 0, and this is the estimate for beta 1. As we know, if we have a different set of data, then we're going to have a slightly different model. And so here we have another example, and you see the coefficients are quite different. For the slope, maybe there's not so much difference. We're talking between 15 and 16. But in terms of the intercept, you see that we go from 0.74 to minus 8.82. So that is a very large difference. If we collect another set of data from the same reality again, we have a different model again, and a different model if we go a fourth time, etc., etc. So the point here is that depending on which data we use to fit the model, we are going to have different results, different coefficients. And so we see there's a certain variability due to the data. Let me give you a more striking example. So here we have 4 data sets about the same variables, y and x1. And the question is, again, if we assume a class of models in which we assume a linear relationship, these are the fitted lines. It looks like there is a negative intercept and a slightly positive slope. And the question to ask is, what are reasonable estimates of beta 0 and beta 1 in reality? So what do you think in reality or in the optimal model those two coefficients would be? Just take a minute to think about it. So let's see, in the first example, we have an intercept of minus 2.8, then minus 1.87, minus 3.16, minus 1.93. So I don't know, looks like maybe a beta 0, let me write it down here. An estimate of beta 0 could be something like minus 2.5, maybe, something like that. And then we have the estimate, sorry, the estimate for beta 1. You know, teaching in the winter is not very healthy for my throat, apparently. So we have 0.37, 0.18, 0.47, 0.35. So let's say that 0.30 something, maybe 0.32, maybe. I don't know. Maybe these are reasonable estimates that we could have for the model, for the optimal model. This is only by looking at the data and by looking at the models that we fit with each of those 4 data sets. Well, it turns out in this case that reality, that of course we didn't know at the time, tells us that y and x1 are actually not related to each other. And in reality, this is the optimal model, the one in which y is completely independent of x1. Trust me, these 4 data sets have been sampled from this model here with a certain degree of error in there, of course. And so the optimal model should be the one telling us that there's basically nothing. So y equals just random error. So beta 0 should be 0, beta 1 should be 0. So essentially, there's no intercept, or the intercept is 0, and there's no effect of x1. And these are, again, 4 data sets randomly sampled from such a model. And you see, the point is that, yes, you might find some negative or positive effect here, negative or positive effect there with a certain magnitude. The question is, how much can we trust that there really is an effect? Have a question, maybe we can use the mean of the values for beta 0 and beta 1. Yeah, exactly. That would be a reasonable estimate, a reasonable way to estimate these coefficients. But again, in reality, think you have to realize that normally you only have one data set, and then you can just fit the one model. So the question again is, if we have the one model and we have these specific coefficients, how much variability do we estimate for them? So can we have some way of estimating how much variability we should find in the estimates? And so let's see, this is variability due to the data, due to sampling data. So let's say that we find a beta 0 that is very close to 0. What does it mean? Well, maybe it means that there is no intercept and that y equals 0 when x equals 0. So that means if you look at the scatter plot, the regression line crosses here the origin. So maybe the true model is something like this. There's no beta 0. And what happens when the slope, the beta 1, is very close to 0? What does it mean? Well, it means that maybe x has nothing to do with y. They are basically independent. So essentially that the line would be flat. There's no relationship with x. So maybe the true model is something like this. There's only an intercept, but there's nothing, no relationship with x1. All we observe is basically random noise. Or maybe it's the two of them together, as we saw in the previous example. But the point is here that we can't just consider whether it's very close to 0 or not. Why? Because if you think about it, again, the magnitude of the betas depends on the units of measurement of the x's and the y. You're going to have different beta zeros if you have your units changed, and that should not happen. So we should try to find a way to quantify this certainty in the coefficients that is independent of the units. So it's not really about the coefficients being very close to 0. It's actually about how much they vary and where they vary across the samples. That's really the point. So it's not really about the sorry, the size of the coefficient. It's about how much we expect it to vary and vary around which values whenever we collect more data, or if we were able to collect more data. That's the point. So again, depending on the data, we're going to have slightly different estimates. But given the current estimate with the current data, again, we only have one data set, only one coefficient. How precise is it? How can we quantify this? We need some way of quantifying this precision of the estimates. And if we think about it for a minute, what are the things that we should expect intuitively from this way of quantifying the precision? First one is that it should be unit agnostic. So regardless of whether I have my variables in kilometers or in meters, we should be able to say the same thing. Intuitively also, the more data we collect, the more precise the coefficients, because we are getting closer and closer and closer to sampling the whole population. So the model should be more stable. Intuitively also, the better the data coverage, the more precise. So imagine that x goes between 0 and 100. If you sample data only around here, you expect the coefficient to be very variable, because you're just looking at a tiny portion of the domain. So intuitively, if we look at the whole domain, we should have more precise estimates. And of course, if the data itself is not very variable, then we should have more precise models. So if, as a property of the phenomena that we're studying, if this random error is not too high, then we should expect the estimates to be more precise. So let's take a look at some examples. Imagine that here we have, again, a simple model of y and x. The black line is reality. Each of the red lines corresponds to a regression line with a certain set of data. Now, what do we expect to be the effect of the phenomena just having larger variance? Sorry. So what is the effect of having larger residuals? And again, this is not something that we can control as the analysts. This is just what reality is. Let's imagine that it's more variable. So what should we expect? It should be something like this. So we should have more variability, for example, in terms of the intercept, and we should have more variability, you see, in terms of the slopes. What happens if we study just a tiny portion of the data? So we have a very small range of X values. Now this is something that we can control, and this is why again the study design is important. Why it's important to very carefully plan how you're going to collect data and what kind of data. Because if you just sample data from a tiny portion of the domain, let's say over here, then you see how much variability you're going to have in the coefficients. It's going to just go crazy. What is the effect of sampling more data? And again, this is something that depends on your study design. Well, we should expect the lines, the red lines, the fitted models to be closer and closer to the true model. So you see, it's again not only about looking at the data and fitting a model, it's about planning very carefully how you're going to collect the data. And whenever you're not part of the decision-making process in how the data is going to be collected, at least it's important that you realize what are the limitations of how the data was collected before you start analyzing. And so same thing happens with the predictions. Given a linear model that we estimated, some f hat, if we have some new data point x star, we can make a prediction. And so the estimate y hat star for that new point, it would be just evaluating the model on that new observation. And this prediction is actually the expected value of the response in that point of the feature space. So it's something like, what is the expected value of the response given that we are in this specific point of the feature space? And unless the model is perfect, there's going to be some degree of error in this estimation. And so where does this error come from? And how can we quantify it? So again, it's not only that the coefficients of the model are going to have a certain degree of error, it's also that the predictions from the model are going to have some degree of error. And so let's look at the linear model as a statistical tool so that we can start answering these questions. And it's all about assumptions. So a linear model that we saw in the previous lecture tells us something about the given data sample, nothing else. It's just a mathematical tool. And if we want to make inferences using the linear model about populations, then we need statistical models. And usually this translates into making certain assumptions about the data, for example, so that we can think probabilistically about the coefficients of the model and the data that we are sampling to fit the model. In the typical case, in linear regression, we assume these four things. The first one is that the residuals they follow a Gaussian distribution. So we impose a very specific distribution on what the residuals should look like. The second thing we enforce or we assume is that the observations are independent of each other. So we have a set of data points. Observation number 1 is independent of observation number 2. They are not correlated in any sense. So for example, if you're measuring the height of people, you have always different people, things like that. And in the case that I told you about as a motivation for the hierarchical models, if you remember, we talked about school and then a class within that school. And then from there we have students, remember? And we could have a test score for each of those students. But the point is that really these students are not independent of each other because they are in the same class. So there could be some kind of class effect in here. These students are not independent of these other students either because they really belong to the same school and there could be some kind of effect of the school. Now we have another school, yeah, maybe you can start assuming that this student is going to be independent of those, but it's going to be a tricky situation because always there's some kind of structure in the data collecting process. But what we assume in the model is that they are independent. We also assume no collinearity, meaning that the predictors are uncorrelated. So there's no correlation between any of the x's. And this is the problem if you remember when we start adding transformed variables. If we have something as a function of x plus a function of x squared, those two things are going to be correlated, of course. And so we are breaking the assumption of collinearity. Still, it's a linear model, but we're just, you should be aware that we are breaking this assumption when we look at it from a statistical point of view. And the other one is homoscedasticity or constant variance of the residuals. And if you remember about it, sorry, when we talked about it, if we plot here the fitted value and here the residual, this should be a random cloud of points. In the example of the TV, we saw that there was something like this, and very clearly here we see a pattern of homoscedasticity. So the variance in the residuals here is very different from the residuals there, so we have a problem of homoscedasticity. And so these are the 4 assumptions that we make when looking at the regression, or the linear model from a statistical point of view for regression. And just FYI, it turns out that if we fit the model via ordinary least squares, like we saw the other day, turns out that we are optimizing for certain statistical criteria. And in particular, optimizing in this way turns out to be a certain kind of estimation from a statistical theory. You can think about it, it's called maximum likelihood estimation. And basically, if we assume a Gaussian distribution, etc., 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 that kind of estimator, it's essentially the same as the ordinary least squares. So that's why we typically do this. So we talk about standard errors again, just like we talked about the standard error of the mean in the previous lectures. So how much variability we expect when looking at the sample mean over different samples. We have the same issue here. So we look essentially at statistic of the model, in this case the coefficient, over different samples. So the sample distribution of a certain coefficient, beta j, is the distribution that that coefficient follows across different training data samples. And by the way, we know that they follow a t distribution because we are assuming Gaussian residuals. So again, the issue here is if we have one set of data over here, we fit the model, then we have a certain estimate, let's say for one coefficient. If we gather a different set of data, we fit the model and we have a different estimate. So on and so forth, different data, different coefficient. What the sampling distribution of beta j is the distribution of all these betas. So what is the distribution of beta j over replications of the experiment? And so this is the sampling distribution. This one is going to tell us how much variability there is in beta j and where is that variability around. And what we saw also is that there's this concept of the standard error, which is the standard deviation of the sampling distribution. So essentially, in this vector that I drew here, what is the standard deviation? And so a higher standard deviation, a higher standard error. Sorry, this thing just. Thank you. Let me come back in a second. Thank you. Yes, sure. Okay, it's a good thing that this is being recorded. So the standard deviation is of the sampling distribution is the standard error. So if we have a low standard error, that means there's not too much variation in the coefficient across samples. So that means there's a higher precision. We don't expect it to vary too much across samples. If we have a high standard error, that means that distribution of the coefficient is very wide. And so for any one fitted model, we can expect a lot of variation in the coefficient. And it turns out that for the simple linear model, we have these very nice equations. So you see, for example, the standard error of the slope is a function of how much variability there is in the predictors and how much variability there is in the data itself. And as you see also, this is proportional to the number of data, so the number of observations. So this would be proportional to n, and so the whole thing would be smaller as n increases. And kind of the same story for the intercept. It's a function of the data and the variability in the model. So we have the standard errors as a way of quantifying how much variability we expect in the coefficients. Given the standard errors, we can also compute confidence intervals for the estimates. So we could have here the point estimate of the model plus minus a certain width. And it's going to be this T sub alpha multiplied by the standard error. What this T alpha is something very similar to what we saw in the previous lectures. Is a value that is going to depend on the amount of confidence that you want to have in the interval. So for example, if we want a 95% confidence, then something like 1.96 or 2 is what we said. So typically we say the estimate beta j plus minus 2 times the standard error. That gives us an approximate 95% confidence interval for what is the expected value of the coefficient. And so again, this is going to give us some interval that with certain probability contains the coefficient. And I should say this is technically incorrect. What I'm telling you is not exactly the probability that the coefficient is contained in there, but it's a complicated thing, and let's not get there. If you really want to know exactly what it means, I'm happy to answer later. But at least you get the notion. With certain confidence, we know the coefficient should be around there. And also we could do hypothesis testing on the coefficients. So just like we did many times earlier, we could just start by setting a null hypothesis. So the null hypothesis would be that the coefficient equals 0, meaning that feature doesn't have any effect in the model. So there's basically nothing. And the alternative would be there is. So as we know, the way to go would be compute a test statistic. In this case, it turns out to be also a t-statistic. And these things should look familiar. So we have the current estimate, we have the value that we are testing against, so in this case the 0. Down here we have the standard error. We compute the t-score, the t-statistic, then from that we compute the p-value. And as usual, if the p-value is less than some threshold, typically 5%, 1%, we reject the null hypothesis. So we could go coefficient by coefficient of the model, testing the hypothesis that they are different from 0 or not, using the typical hypothesis testing framework with p-values. So let's see an example. Here we have the model of the sales of the product as a function of the advertising on the TV, and the ordinary least squares model was this one here. So again, this is the coefficient beta 0, beta 1. And if we now assume Gaussianity or the Gaussian distributions, we assume uncorrelated predictors and everything, we can start computing all these quantities of the variability in the model. So we have the standard error of beta 0 is about 0.45, the standard error of beta 1 is about 0.003. So this already gives us an idea of how much variation we should expect in these numbers here. And as you can see, of course, the standard error for beta 0 is larger because the coefficient is larger to begin with. And we could have also something like 95% confidence intervals. So we know with a 95% confidence that the coefficient beta 0 should be somewhere around 7, which is the point estimate, plus minus 2 times the standard error, so plus minus 0.89. And again, this gives us some idea about what to expect from the coefficients in any replication of the process. We could also have something like 99% confidence intervals, and essentially that means that they're going to be wider if you compare those two numbers. So of course, if you want the interval to contain larger confidence, then it's going to be wider. And we could test hypotheses. So we could compute the t-test for beta 0 and see that the p-value is very, 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 very small. So we have evidence here that the coefficient is indeed different from 0. So we can start doing all these things for every coefficient of the model to try to quantify whether there is really expected to be an effect of the variable or not. So all these things, the precision of the coefficients, depend on what other variables are included in the model. Again, so if you remember, we had a model of a single predictor, the TV, and then we had a model with TV, radio, and newspaper. And what we saw so far in the previous lecture was the table up to here. Now in this lecture, we can start adding more columns. And if we look at them, then what we see is that, for example, the standard error for the intercept changes because also the estimation changes. More importantly, we see that the standard error for the TV was 0.03. And now the standard error for the TV is 0.001. It's smaller, and it's smaller because we are now explaining better the relationship between the predictors and the response. We're explaining more variance in the response. And essentially what you see is that the numbers are going to change. The p-values, the t-values are going to change depending on what other variables there are in the model. So again, be very careful with interpreting the coefficients just in isolation without looking at everything else in the model. And in fact, we're going to see that it's very common that something that apparently is statistically significant, like this one, if you start adding more variables into the model, then maybe suddenly it's not statistically significant anymore. And that makes total sense. It's normal to find that. So we have to be careful when looking at these coefficients. And the same thing applies, exactly the same thing to dummy variables. And think about it. So what does it mean that we have the coefficient for dummy variable equals 0? Then that would mean that that particular deviation would be 0. So that would mean that whatever group this variable j is representing, it's not statistically different from the baseline. So in this case, we have the wage of employees as a function of their marital status, and we saw that the baseline, the coefficient rate 0, corresponded to people never married. And then all the other estimates were deviations from it. So if you want to know the average of divorced people, it's actually 92.7 plus 10.4. And so if one of these coefficients we tested and we claim it to be equal to 0, then what we're saying is that this group is not statistically different from this group with respect to the wage. And so in this case, for example, what we have is that there is a very clearly significant effect here of the coefficient for the married people. So we know that married people have a different wage from non-married people. However, if we look at p-values over here and standard errors, we see that people who are widowed are not statistically different from the intercept, which corresponds to the never married group. So this model is telling us something about differences across groups in this case. And of course, everything changes if we don't fit the intercept. So if you remember, we could decide not to fit an intercept and just have a dummy variable also for the first group, also for the never married group. And then essentially the interpretation of these coefficients is going to be different, because while here we were measuring all these as deviations from the baseline, and therefore these p-values and these standard errors correspond to coefficients interpreted as deviations. In this case, they are not deviations anymore. So what we are testing here is the hypothesis that each of the coefficients is different from 0, which means the mean value of the response for each of the groups is different from 0. So of course now here everything becomes statistically significant, because what we're testing is that the weights of each of the groups is different from 0. And of course they are. What we are testing here is whether the deviations from the first group are different from 0. So you see, you have to be careful how you interpret the statistical part of the table, the standard error p-values, depending on what exactly you are modeling with your coefficients. And of course, the same thing applies to interaction terms. In this case, we had a function for the wage in terms of health insurance and the class of job, industrial or IT. And what we saw is that we could model the interaction. So there is a main effect of insurance, the effect of the information or industrial class, and then the interaction. If we look at the statistical part of the table, again, we see that everything seems to be significant except for the interaction. So what this means is that the difference between insurance yes and insurance no is the same between classes of job. So for example, this distance here is not different from that distance there in terms of the mean scores, whatever they are. And likewise for comparisons across health insurance. So what this is saying is, yes, people with insurance have a different wage from people without insurance. Yes, people in IT have a different wage from people in industry. We can be certain about it because we see that these coefficients are very precise, but we cannot claim a interaction effect. We cannot claim a difference across groups because there appears to be too much random error in the model to really say that this is different from 0. So normally what one would do is just refit the model, ignoring that one coefficient, because we don't have enough evidence to say that it really is different from 0. And again, just like we saw, the uncertainty in the coefficients kind of propagates to the response. So we know we can quantify the uncertainty or the random error in the right-hand side of the model. Of course, whenever we evaluate the model with some new test observation, that uncertainty is going to propagate to the left-hand side, to the response. And so whenever we have a prediction, when y hat, that prediction also has a sampling distribution and also has a standard error. And we can quantify it. And so this allows us to compute interval predictions in addition to point-wise predictions. So not only say that our estimation for that one specific data point is going to be this one, but this one plus minus a certain interval. And let's talk about two kinds of intervals. Let's talk about prediction intervals and confidence intervals. So prediction intervals are intervals about new observations. So they pertain individual observations, while confidence intervals pertain to the mean response of the model. Let me show you with an example what it really means. So we have here a model of the wage of employees as a function of their age. In blue, we have the model. Let's assume just a linear model, no transformation. That's what the model looks like. Now, if we're interested in making a prediction for individual employees, then we are in this case. We're making a prediction interval because we talk about individual observations. And then what we're saying here in the model is that with 95% confidence, the dark red, the new observation is going to be within that interval. And if we want a larger confidence, say 99%, then we would have this interval around here. And again, this is about individual observations. So what this is saying is that outside of this interval over there, we should expect about 5% of the observations in any given data set. So this is about individual people. If we want to talk about the average of the model, so what is the expected prediction of the model for a given value of the independent variable, then we have what we call a confidence interval. And the idea is basically the same. It's an interval that goes around the regression line. It's just that it's going to be a lot thinner. And so what this is saying is we don't expect in this case too much variability in the regression line because we see the intervals are very small. So if you will, you can look at this interval, the confidence interval, as the interval covering the regression line. So if we were to collect new data, where do we expect the regression line to be around? And again, the regression line models the average of the responses. If we are interested in individuals, then we have intervals like this, prediction intervals. So if you think about it, this one is making an interval about individual observations. This one is making an interval about models, about the average response of the model. And of course, you see here what the effect of transformations is. It's just the same thing, an interval above and below the regression line. So we expect a certain probability to be there and to be there with any given observation. And we have a similar thing here with the confidence interval, with the interval for the models. And to give you just one more example of the difference between one and the other, let me tell you about this real case. So what we're looking at here is a plot from this paper. It's from 6 years ago, and it's a paper in which they were correcting the Federal Drug Administration of the United States in terms of the recommended intake of vitamin D that they recommend to their citizens. So via this plot, they were making recommendations for people in the US and Canada about how much vitamin D they should take every day. And what we're looking at here is the intake of vitamin D, so how much you take every day. And over here we have the levels of vitamin D in your body. So of course, the more you eat, the more vitamin D you get. And each of these points corresponds to one independent study. So there were 32 studies in which they were trying to answer this question. And they plotted them here. So again, let me type here. This is one study, the average of one study. So that study found that on average, when you intake something like 1200 units, your level is about 90. And so what they did was fit a regression line. You see it here. And they plotted a prediction interval in there. And then based on this, they said, well, we want to be sure that 95% of our population has the correct level, or to make a recommendation suitable for 95% of the population. So what they did was look at the lower end of the interval. This is what we want people to be in terms of the y-axis. So let's make this recommendation of 600 just to be sure. So they wanted people to have at this level. And so they recommended 600 units of vitamin D intake. Again, this was the official recommendation. And then some statisticians realized the mistake. If you make this interval, you are referring to study averages. So this interval is expected to cover 95% of study averages because each of these observations corresponds to one average. So what this means is if you keep running these experiments over and over again, then you're going to have with 95% confidence that the average of this study is going to lay within the interval. Not individual citizens, but averages over citizens. And so what they did was try to correct that by looking at what the interval should be for each of those studies individually so that they cover citizens instead of averages. And what they estimated was that they should be around here, each of those points. And then they refitted the model, this red line, and this became the correction for the recommendation. So you see, if we are aiming for a level of 50 again, we are not even close with 600 units of intake. We should actually go far larger. It's not even shown in the plot. It should be about, I don't know, 5,000 units. So the point here is, again, this is something that it's very easy to misunderstand. Each of these points corresponds to an average. So whatever confidence we have here is about averages, not about people. So in a sense, in this case, they were talking about confidence intervals. So they were talking about averages. In this case, they were talking about individuals. So this is a prediction interval. And you see what is the difference between the two of them and how that can lead to very wrong conclusions, like in this case. So I think it's time to make a break. It's 11:33. So let's come back at 11:45. So 12 minutes, and then we continue with the rest of the lecture. If you have any questions, feel free to post them in the Q&A, and I'm going to start answering them now. So see you in some minutes. Okay, we are back. So let's talk about using the linear model to compare group means, to test hypotheses about group means. Let's see. So one hypothesis that we could have is if we only have one group. And so the model would be essentially the mu, the mean in the population, equals a certain constant. So for example, we could think about testing the days to recover of patients. We're just interested in figuring out what that mean is. We could be interested in comparing between two groups. Let's say group A and group B in an unpaired way. And unpaired, that means that the observations in one of the groups are not related to the observations in the other group. So it's essentially about different items. You can think, for example, the response would be the days to recover, the treatment A or the treatment B. Those are the two different groups. And we're just talking about different patients. So there's no relationship between patients in group A and patients in group B. If there is a relationship between the items, then we talk about a paired case. So for example, we could be interested in testing differences in score tests for the same students. And the two groups, the two conditions would be the beginning of the course or the end of the course. So what this means is that every observation in group A is linked to an observation in group B. So we could actually put them in pairs. So for this one student, we have the test before and the test after. So this is what we call the paired case. And the nice thing about it is that we can essentially reduce the random error by modeling this second factor, which is the student. So essentially, in this case, we could have just y as a function of the treatment of the group. In this case, we can have y as a function of the group and the student of the item. And by including this second factor, we are going to be able to reduce the random error, so it's going to be better. And of course, we could look at the cases in which we have more than two groups. So we could have m groups, an arbitrary number of groups, in the unpaired case, and the same thing in the paired case. So again, something like if we have multiple treatments in different patients, that's an unpaired case. Or in the case of students, we might be interested in testing students at the beginning of the course, the midterm, and the end of the course, so that we will have three different groups or three different moments to test. So what we're going to see is that, of course, you can just look at the data from a descriptive point of view and compute averages and everything. But if you want to start again making sound claims accounting for random error, for variability, then you have to start building models around it. And the linear model is actually something very useful in these cases. So let's see. Let's go to the case again in which we only have one group, and we're interested in testing the hypothesis of whether the population mean equals a certain constant C. So let's say we collected some data. Here we have the histogram, and we're testing the hypothesis. This is our estimate, so this is y hat, what we tested, or sorry, what we observed in our sample, and we want to test against a certain constant. So if we conceptualize this problem, then what we're saying essentially is that the variable y is a function of basically nothing. There's no relationship with any other feature or factor. We're just interested in describing the response y, and in particular, we're interested in the mean. So one way to go around this problem would be set hypothesis. So we say the null hypothesis is the mean mu equals the constant. The alternative hypothesis would be it's different. We can run a test. In this case, it would be again a t-test. And you see here how to compute it again, as usual. So we have the observed value. We have the value that we're testing against, the standard deviation of the data, and the number of observations. And this in particular, we're going to see is the standard error of the mean, what we see, or so actually in a few lectures back. So if we test it, then this is what we get. We look at the estimates. So what we observed in the data set is 0.487. This is the sample mean actually for y. This is the mean of y. Here we have the test. 3.3 is the t value, and the corresponding p value is this one here. So this will be the way about testing this hypothesis. Turns out that this corresponds to the following linear model, one in which we say the response is just a function of the intercept. So we're essentially just saying we have the mean value for me and random error. And so if we fit this model and we look at the table, what we have is that the intercept has an estimated value of 0.487, which you see is exactly the same thing we had here. We have the standard error, the t-value, which corresponds to the t-test, and of course the p-value, which corresponds to the p-value there. And so what we see here is that the test statistic is actually involving the coefficient that we are estimating in the model by beta 0. This is against the 0, the value that we're testing, and this number here corresponds to the standard error of the coefficient. So it would be this quantity here. So what I'm showing you here is that in this problem of testing the mean of a population, what we are doing is essentially testing for a coefficient of a linear model. It's exactly the same thing. If we run a t-test to make that or to test that hypothesis, under the hood, really what we are doing is fitting this linear model and looking at the coefficient beta 0. Let's go to the case in which we have two groups in the unpaired case. So think about students, test A, test B. Sorry, not students, treatments. So we have patients in one group, patients in the other group. So we collect some data. We have group A in red, group B in blue, and these are the histograms, and the dashed lines are again the estimates. And so from a conceptual point of view, what we're looking at here is the case in which the response, Y, is a function of the group. It's determined by whether you are in group A or group B. And of course, we can start setting hypotheses again. Null hypothesis, the mean in the two groups is the same. Alternative hypothesis, the mean is different. The way to test this hypothesis would be again a t-test. And in this case, I'm assuming, as you can see here, certain things, but for illustration purposes, it's fine. So what we have is the mean in one group minus the mean in the other group, and then again, the standard deviation in the response and the number of observations. If we run this test, what we have is the following. So here's, from a descriptive point of view, the mean in group 1 or A, the mean in group B, the t-statistic, and the p-value. This would be again evidence against the null hypothesis, so we would conclude that there is a difference between group A and group B in the population. If we look at this problem from the point of view of a linear model, really what we're doing is the following. So we have one categorical variable telling us whether the observation belongs to group A or group B. And as we saw, this corresponds to a dummy variable for the case of X equal B. And so what we're testing here is group A corresponds to the baseline, beta 0. Group B corresponds to beta 0 plus the deviation beta 1. And exactly the same thing is what we're doing here. If we fit the model, this is what we get. We get the estimate for the first group that you see corresponds to what we saw here. We had the deviation from it for group B. So you see, if you add these two things together, you get this one there. We have the standard errors, t-values for each of the coefficients separately. And specifically, the one that we're interested in is this one for group B, the one that tells us how different is B from A, what is the deviation. So essentially, what we're looking at is this t-statistic, you see, and the p-value is the same. So if we look at the formula again, what we have here is beta 0 plus beta 1, and the standard error of beta 1. So what we're looking at here is the deviation compared to the error in the estimation of the deviation. So again, as you remember, I told you some time ago, everything in hypothesis testing is about the magnitude of what you observe, the magnitude of the effect, compared to the magnitude of the error. And this is once again what we're doing here. So in this case, also you see that if we test for the mean of two different groups, really what we're doing under the hood is just fitting this linear model and looking at the test for beta 1. It's essentially the same thing. If we go to the paired case, again, you can think about students and scores. So let's say here we have the test in the beginning of the course, and here in the end of the course, each point corresponds to a student. So we can plot scatter plot. And we have the estimates for group A and for group B. Conceptually, what we have in this case is something like this. The test score depends on whether you are in the beginning of the course or the end of the course, and also depends on the specific student. We can set hypotheses again if we want to test group A versus group B. And the test to run is again a t-test. It's just slightly different because now here we have the standard deviation not of the responses, but of the differences in the responses. So if you think about it, we have one vector for group A, we have one vector for group B, and essentially what we're doing is computing the vector for the difference, and the standard deviation here refers to that one there. And so if we run this t-test, what we have is, again, the same estimates as we had, and the p-value we see now is different. So in this case, we would not have enough evidence to claim that the scores of the students are different between the beginning of the course and the end of the course. Well, if you think about it, what we have here is one categorical variable and another categorical variable. And we know we can build a linear model with multiple categorical variables. So the linear model would be something like the global intercept, of course, and then a deviation for it or from the baseline when we belong to group B. And then we have deviation for item 2. In this case, it's student, and there will be a deviation for item 3, 4, 5, etc., etc. So we are essentially modeling both categorical variables. That entails including multiple dummy variables in the model. If we go ahead and build the model, then what we have is something like this, and of course many more coefficients down there. So we will have beta 0 corresponding to the score of item 1 in group A, and then we have a deviation in general for group B. And then we will have deviation for item 2, for item 3, item 4, etc., etc. Each of them with their corresponding statistics. And so what we see here is, again, a certain deviation between group B and group A. And if you look at the t-statistic is the same, the p-value is the same. So yet again, what we see here is that these comparisons between groups, let me clear here, running the test, what we're essentially doing here is, again, this is beta 1, and this is the standard error of beta 1. So again, we are just building a linear model. Under the hood, even if it's not immediately clear, what we're doing is build a linear model and then test the coefficients. And that is going to give us the solution to the question of whether there are differences between groups or not, controlling for the students, in this case for the items and things like that. And the question is, what happens when we have more than 2 groups? Because if it's only group 1 and 2 or A and B, we can just look at this one coefficient, this p-value, and that's fine. What happens if we have more than 2 groups? Then we can use something called ANOVA, analysis of variance. And the idea of analysis of variance is that it partitions the total sums of squares, so the total variability observed in response, into sums of squares or variability kind of coming from each of the factors that we are including in the model. So in this case here, how much variability in the response there is because of differences across groups, and how much there is because of differences across items. And so depending on that, on how much variability there is among the mean scores of the levels of a factor, then we are going to be able to answer different questions. So if we find that a certain factor has a lot of variance, then that means the groups that belong to that factor are clearly different. So this factor can explain a large portion of the observed total variance. So let me illustrate a little bit. So imagine here we have the response, and here we have the mean for group A, here the mean for group B, mean for group C, things like that, mean for group D, etc., etc. What we're doing here is quantifying how much variability there is across these means. Now imagine that instead of that, we had something like this. Mean of A, mean of B, mean of C, mean of D. So in this case, the variance is larger. In this case, the variance is smaller. And essentially what we're saying here is that the response across the groups are closer together. The response across the groups is farther apart. And so there is a larger variability due to this factor here than there is here. That's what ANOVA is going to do for multiple factors at the same time. And so if your hypothesis is about the mean scores across different groups, in this case, it will be more clear that there are differences. In this case, it's less clear that there are differences because these departures could be just a product of the random error. And so if we observe a variability that is small, then that means the groups are not apparently different, like we had in the right-hand side. So it's likely that the factors don't affect the response. And of course, somewhere in between, there are many shades of gray. What matters really is the relative comparisons between the factors. So which factors are responsible for the largest variability in the response? And by the way, ANOVA is a topic that is huge. We could have a course only on ANOVAs, but that's not the point here. So if you start reading about ANOVAs, you're going to see that there's plenty of material about it. But here I'm just taking a simplified take at it. So let me see the difference between looking at the coefficients of the model and looking at an ANOVA table. So if we had this model in which we have the wage of employees as a function of their age, the year of the measurement, their marital status, and whether they have insurance or not. If we look at the coefficients, then we might ask two questions. First, what are the factors that are more important in this model? So which of these factors are responsible for the largest variability in the response? Well, in principle, one could say, well, let's look at the magnitude of the numbers. So this one seems to be the largest, followed by that one. So maybe whether people have insurance or not, that's the one. But again, think about the estimates. They are dependent on the units. So these comparisons don't really make too much sense. So I don't know, maybe we should look at the standard errors. Same thing. We should look at the p-values. But again, this p-value, for example, corresponds to a deviation from the first group, which is the not married, which is encoded in the intercept. But the intercept is also encoding the case for insurance yes. So it's not clear at all how to answer this question. And what about this hypothesis? The hypothesis that people never married have a different wage for people married, widowed, etc. Again, we have here coefficients that we can interpret only holistically looking at the whole table. So there's a certain effect here of the class of job, or sorry, the insurance. There's going to be some degree of confounding in here. So we have to account for all these things when making such questions. The way to do it is look at an ANOVA table. And the ANOVA table looks something like this. So you see, instead of having now one line per coefficient of the model, we have one line per factor of the model. So instead of having multiple rows for the marital status, we only have one over here. So what this is telling us is each of the factors in the model, how much variability are they responsible for? And that's what we see over here. And so what we see is that the one that has the largest sums of squares is the insurance. We can look at the F scores here. The F score is something like the generalization of the T-score for more factors. And in fact, you have this nice property here. When there's two factors, T-square is the same as F. But anyway, so over here, what we're testing is this hypothesis. Are all the means across the groups of the factor the same? And what we have is, for example, in the case of insurance, we see that no, there appears to be at least one of the groups which is different from the others. And in terms of marital status, at least one group is different from the others. So here, these p-values are giving us the answers to this hypothesis about multiple groups. And the f-values and sum squares are giving us answers to the questions of which factors seems to be the ones having the largest impact in the response. It's actually the insurance and the marital status. So that's the difference between looking at the coefficients of the table and something like the ANOVAs. If you want to answer these kind of questions, then you cannot look at the coefficients. You can look at the ANOVA tables. Okay, and let's talk just a little bit about model selection. And it depends. So on what purpose do we have for building the model? Are we interested in building the model for understanding or for predicting? If what we want to do is build a linear model for making predictions, and the prediction is all we care, how accurate the prediction is, then typically what we do is we use all features. So all the features that we have in the data set, we just put them in the model and let it do its magic and make the best predictions it can. And what we do is measure the model performance with out-of-sample metrics. So test sets, essentially, cross-validation, things like that. So we're interested in the predictive accuracy of the model. So we test the model on data that it didn't see during training. And it's just a matter of using as much features, as many transformations as you want, just to get the best accuracy in the prediction. If, on the other hand, you are interested in understanding the data and testing hypotheses about how different factors affect the response, maybe hypotheses about interactions, then we have to make certain decisions. And what we have to see here is that fitting a good model is an iterative process. It's not something that you just do the one time. It's something that you have to adjust and remove variables, add variables, transform variables, etc., such that you get a model that is as faithful to reality as possible, and it accounts for as many of the possible factors that you can control for. So, what predictors, what features should we start with? If you have certain domain knowledge, you can start by building a model using domain knowledge. So, what are the factors that you expect to have an effect on the response given your knowledge of the problem? And then from there, you can start, refining the model. Maybe you could start with a pre-specified hypothesis. So if the hypothesis really is about, the recovery time of a certain surgical procedure, then of course you start with including the variable referring to the surgical procedure. And then you will see that you can start controlling for the sex of the patients, the age, etc., etc. And you will see whether those factors have an effect or not. If you just have data and nothing else, you can do exploratory data analysis and try to see where there appears to be patterns, and then try to build a model around those patterns to see if there really is something there or not, or it's just, random error. And if really there's no indication whatsoever about what factors to include in the model, what you could do is build a model with all of them, and then look at the ANOVA table and start with the factors that have the largest influence in the response. So in this case, I would include these two to begin with because they appear to have the largest influence on the response. And again, you're going to reach a problem in which you ask, what is the best combination of features? Out of the many possibilities, which one is the best? Ideally, we could fit all the possible models with all the possible combinations of features and transformations and just select the best one according to some criterion, like R-square or the Akaike information criterion, things like that. The problem is that this becomes really impossible as we increase the number of features. It's just impossible to fit all the possible combinations. And so you have to find some way to try to simplify a model or try to build a model that looks kind of good enough. And we're going to talk about two selection procedures that are traditionally used, although they're really not much recommended nowadays. But anyway, I'm going to tell you about them. And they're forward selection and backward selection. The idea in forward selection is that you start with a model that contains no feature. It's only the intercept. So essentially what you fit is this. And it's just about fitting what the average is of the response. And then the idea is you fit separate models P separate models by adding each of the predictors individually. So you're going to have one model being y as a function of x1, another one y as a function of x2, y as a function of x3, etc., etc. And then from those three models, you keep the one that is optimal in some sense. So for example, you could choose the one that has the highest R square. So let's say that you look at all these models and the one with x2 is the one with the highest R square. So we keep x2. And then the next thing to do is feed the p-1 remaining models that retain the x2 and then include one of the other variables. So you do y equals x2 and x1, and then you do f equal x2, x3, etc., etc. So all the two variable models that include x2. And do the same. Choose the one with the highest R square, for example, and then continue until you reach a point in which some condition is met. So for example, all the remaining variables have a high p-value. They don't seem to affect the response, and so that's it, we stop. Or if we have an R square that is already good enough, or if the increase in R square is not substantial. So the idea is to start adding variables to the model, in each case making this greedy selection. So without looking back and forth, we just make the best selection at the point. And we could do it also backwards. So we could start with the maximal model, the one that includes all the predictors. So essentially the y as a function of x1 to xp. And then the idea is remove the predictor that meets some conditions. So for example, the one with the largest p-value. We look at the regression table here, we locate the feature with the highest p-value, and we just remove it. And then we refit the model without that one variable. Again, we look at the table and see which is the feature that now has the highest p-value, and then we remove it. And we continue this way until, again, some condition is met. So for example, all the remaining predictors have a small p-value, and there's no reason to remove them from the model because they seem to have an effect on the response. So this is called backward selection. So again, forward selection, we start with the intercept and go forward. Backward selection, we start with all features and go backward by removing features. And the reason why they are not really recommended is that they have a number of issues. The most important one is that the optimal model is not guaranteed to be found in any way, because the process is what we call greedy, meaning we make the best decision at each point without looking back or looking forward. And so we are not guaranteed to find the optimal model. And it turns out that the coefficients are biased away from zero. This way of selecting the model is biasing the coefficients away from zero. And so as a result, the p-values are biased towards zero. So the models are biased towards giving us more confidence that we really should have. And in general, the R-square is going to be biased towards 1. So the models are going to appear to be better than they really are. And nowadays, we can use more advanced methods. There's one thing that we call regularization, which is essentially going in this direction about selecting features and how much impact each of the features can have. If you want to look at it, look at the lasso regression and ridge regression, and you're going to see the ideas behind it. And something else that we could do is just do dimensionality reduction, which is something that we will see in 2 lectures, which is about reducing the dimensionality of the data set to begin with. So instead of trying to feed a regression model with 1,000 variables, we try to do some magic and reduce the data set to only 10 variables and then feed the model with only those 10 variables. We'll talk about it in 2 lectures. And of course, there are other things that we could do. We could try cross-validation and try to see, what the effect is of each of the variables on an unseen set. Of course, we can always leverage domain knowledge, and if we have certain knowledge about the effect that one factor is expected to have on the response, because I don't know, some theory says so, you go and include it. And of course, we can select from several pre-specified models. We look at the R-square, the AIC, BAC, adjusted R-square. We can always look at these statistics for model fit. But regardless, what you should always do is look for patterns in the residuals. So always plot the residuals against the fitted values and look for patterns. It should look like a random cloud of points. It should be random. That is the point. If you see non-random shapes, that normally indicates the need for transformation. And if you see clustered data points, that normally indicate the need to include other variables that you're missing in the model, other variables that are responsible for that pattern in the residual. So something that we are missing. And really looking at the residuals plots is going to be more informative than just looking at hundreds of tables with hundreds of the numbers. This is my suggestion anyway. Okay, and then finally, I want to talk a little bit in brief about the generalized linear model and logistic regression in particular. So the problem with the basic regression model is that it assumes the responses are distributed according to a normal distribution, according to a Gaussian distribution. This was the first assumption that we saw. But in many practical applications, this is of course unreasonable. So think about cases in which we have ordinal responses or the response is bounded between 0 and 1. So think, for example, that the response is some kind of a ratio, some kind of fraction. There's something called generalized linear models that are an extension of the general linear model that we saw. And what they allow us is to account for other distributions. So not just the normal Gaussian distribution, but some other things. And they're actually built with two components. The first one is we add a distribution D for the response. And we add a link function G between the response and the predictors. So let me show you a little bit of examples. So the generalized linear model looks like this. There is again the link function that transforms the response. And now we're going to see that the residuals follow a certain distribution D. It's not going to be Gaussian, but it's going to be something else. And it turns out that for the Gaussian case, what we have is just the identity. So the transformation of the response is just the response itself. And the residuals follow a Gaussian. That's it. We have a linear model. If we deviate a little bit from it by making a selection either here or there, we can start doing something more interesting. So for example, if we want to model proportions, so that is a response that is between 0 and 1, what we can do is use the logit function in G. The logit function is essentially just measuring the log of the odds ratio. So because Y is a probability between 0 and 1, this thing is the odds ratio, and then we apply the log. And what we are going to assume for the distribution of the data is a binomial distribution. A binomial distribution that is essentially just counting zeros and ones. If we have a different case in which the response models count, so for example 0, 1, 2, 3, 4, 5, just a count of things, we could use a Poisson distribution and a log function for the link. Let me focus here on the case of the binary response, something that is between 0 and 1. So if we have a bounded response between 0 and 1, then again, as I said, we choose a binomial distribution for the residuals, and that is essentially telling us the proportion of zeros and ones. And the link function takes this shape. This is how it's transformed. So what it does is it takes the original response between 0 and 1, and it transforms it into a response that goes between minus infinite and positive infinite. So it's essentially taking values between 0 and 1 and stretching them so that they cover the whole real line between minus infinity and positive infinity. And the reason to do this is that we are going to do regression on the transformed variable here between minus infinity and positive infinity instead of in the original variable. And there's a reason why we do that. So the linear model is going to again be fitted here in a transformed space. And then the link function just transformed the original y into the logit of y. So the logit function is a sigmoid, as you saw. We call it sigmoid because it has this kind of S shape that maps a probability in 0, 1 onto negative infinity, positive infinity by transforming the odds ratio. So again, we have here the logit of a number between 0 and 1. It's just the log of the odds ratio, and it gives us a transformed value. If we want to transform back, we can just do the inverse logit, and we have the response. And the reason why we do it is that this transformation is going to allow us to fit a linear model between negative infinity and positive infinity, therefore getting rid of the problem of the bounds. And then whenever we want to look at the prediction from the model in the original scale between 0 and 1, we just transform back. So the idea is that from the idea of the generalized linear model, we have a function of the response is just a linear model. So everything here in this right part is essentially the same thing we have seen so far. We could put in there numerical variables, categorical variables, interactions, whatever. The only thing is that we are transforming the response. In the case of logistic regression, again, in which the response goes between 0 and 1, this means in particular that we use the logit function here to transform the response, and then we fit the model on the transformed response. So this fitted model is modeling between negative infinity and positive infinity. And then if we want to make a prediction in the original scale between 0 and 1, what we do is we take the model, we evaluate it, and just transform back using the inverse logit. And again, the reason why we apply transformation is that we can fit a linear model all the same without problems in the transformed space, in the link space. And then whenever we want to have the original response, we just transform back. So the model specification is the same as in regular linear regression. Everything is the same. We have the estimates, we have standard errors, we have p-values, we have interactions, we have absolutely everything. It's all the same. So this logistic regression is going to be very useful as an exploration tool for a categorical response between 0 and 1, or something that is a binary response. It can be only 1 or 2. So things like a male, female, things like that. And so let me show you an example. Here we have data about houses in Amsterdam. So what we have here in the x-axis is the value of the house. Each of these points, by the way, corresponds to a neighborhood. And so what we have here is the mean value of the houses in the neighborhood, and what we have in the y-axis is the fraction of social houses. And what we wanted to see is if there is any relationship between those two. Now, the problem is that this response is bounded between 0 and 1. So if we fit a regression line just as usual, we're going to see that for certain values, the prediction is going to be negative, and for some other values, the prediction is going to be larger than 1 or not even get close to 1. So the problem here with applying linear regression just as usual is that we have this trouble around the bounds. We are making predictions that don't make any sense. So what we do with logistic regression is just transform the response such that we don't fit a line anymore, we fit an S. So if we prolong this a little bit, what we're fitting is this S shape. So everything is going to be bounded between 0 and 1. And in this case, you see that we have a somewhat better model for what the relationship is between these two variables. So let me see. What happens if we get this data and we just apply, or we just want to fit the model with the main effect of the house value? So what we saw is that the class of models would be something like this: the logit of the fraction of social houses, that's the response. It has an intercept and it has a slope for the value. Then again, what we're doing is transform the response and then fit the model, the linear model, in the response space. So what we see here is in the link space, in the transform space, we are modeling the logit of the social houses. And so it goes between minus infinity and positive infinity. And this is just a line. We are fitting a regression line in this transform space. When we transform back, it turns into this S-shaped line. But we have exactly the same thing we had earlier. We had the coefficients, estimates, standard error, test values, and p-values. And so we here could test hypotheses about each of the factors in the model, just knowing that we are testing in the link space, because that's where we build the model. We can, of course, include a categorical variable, and that will entail, again, just two different lines, right? One for group A, one for group B. So what we have here is a categorical variable telling us the degree of inconvenience caused by neighbors in this neighborhood. So is it high or low? And again, we could just fit the model. So in this case, what we have is a deviation for the case of low inconvenience. The interpretations of the coefficients are essentially the same in this transformed space. And what we see is that in this case, this variable doesn't seem to be statistically significant. And actually, if you look here, the two regression lines, they seem to be kind of overlapping. So it appears that this one factor, the degree of inconvenience caused by neighbors, doesn't have an effect on the response. So you could decide to just take it out of the model. But the important point I'm trying to make here is the model in the transformed space is just the same that we have seen so far. We can do all kind of magic we want here. It's just a matter of then transforming back to the original response space. And again, we see that these two lines would correspond to these two regression lines here with an S shape. Of course, we could have interactions. It's just the same. So here we have an interaction between the two, and that would correspond, as we see in the link space, to two slopes and two intercepts, which corresponds to these two shapes in the original space. So you see, the generalized linear model allows us to just go beyond the assumption of normality and just look at variables, like in this case, which are fractions. The trick is all the time the same. Transform the variable, feed the model, the linear model, in that transformed space, and then whenever we want to look at predictions, we come back to here, to the original space. The model specification and the interpretation of the coefficients is just the same. And then for prediction, again, given a fitted model, we can just make predictions for new observations, just like in linear regression. And it's just a matter of what kind of prediction do you want? Do you want the prediction in the response space, so between 0 and 1, or are you interested in predictions in the link space? And sometimes we are interested in predictions here in the link space if we are trying to inspect the model, diagnose the model, see what's going on with it, and maybe make some correction by looking at here. So if you want to refine the model, normally you look at this space. If you want to make, just regular predictions, you look at this space. And just in passing, another extension to the linear model is what we call the generalized additive model. I'm just gonna spend 1 minute in this slide. So there's something called generalized additive models, and what they do is they allow for flexible non-linearities in the variables themselves. So it's not only a non-linearity thanks to the link function here, but also non-linearity in each of the predictors. So instead of fitting one coefficient for the predictor, we're going to fit a full function for the predictor. And these functions I'm calling as S because normally we use smoothing splines. And if you don't know what a smoothing spline is, it's essentially a non-parametric function that is allowed to wiggle around with a certain degree of flexibility. And so what we're doing here in the generalized additive model is just the same. Depending on the response, on the type of response, we have a link function and some distribution for the residual. But instead of having individual coefficients for each of the features, we have one full function that is trying to model this nonlinearity between the function, the feature, and the response. And so the thing is that it's going to allow us for a lot more flexibility. And here we have an example. So let's say we want to model again the weight as a function of year and age, etc. And if we do it, what we see is that this first function, this is the smoothest spline for the year. So you see it's modeling this nonlinearity very clearly. Then we have another function for the age. And what we saw earlier is that we were trying to model it as a quadratic term, but it turns out that it's not really just quadratic is something else. So here we have a spline modeling this little bump over there, and a non-quadratic relationship. So the point is, the model is actually going to contain the intercept, of course, this smoothing spline and this smoothing spline, and then it's all about putting them together here for the sake of making predictions. So this one is going to allow for a lot more flexibility because we are trying to model in a non-parametric way the relationship between each of the variables and the response. And there are many other ways of doing regression. So for example, in the case of ordinal logistic regression, in which we have an ordinal response, then what we fit, or the model that we fit really is the logit of probability of y being less than or equal to some of the values. So we fit the model for each of these quantities. So we have, I don't know, from 1 to 3 possible values in the ordinal response, so something like low, medium, or high. Then we fit these separate models for the probability of y being less than low, less than mid, less than high. And it's just the same idea. We fit a logistic regression model for each of those levels. We have multinomial regression, which is the case in which the response is categorical. And then essentially what we're doing here is fit the model for the logit of p saying y being equal to j. So for the model in which we have the response equal to one of the categories versus the others. And so we fit many different models, one for each of the categories, and it's just about putting those models together. We're actually going to talk about these two a little bit in the next lecture. There's lasso regression, ridge regression, loss regression, and they're all in the direction of allowing for more flexibility in this case, and taking care of model selection in this other case. Anyway, if you want to read a little bit more about them, many other ways of doing regression, you have pointers here in the end, of course. So today we talked about the variability in the model and how we have to account for it through standard errors intervals of hypotheses. We saw how comparing means, statistically comparing means across groups is essentially the same as building linear models. And then we talked a little bit about how to build a model and logistic regression as an example of a generalization, a very popular generalization of the linear model. If you want to continue reading about this topic of regression, I suggest this one is also from the last lecture, chapter 3.3.3 on potential problems. I suggest you go to chapter 6.4 for considerations in higher dimensions. This is also suggested from the models lecture. And in the lab, you're going to do regression using the stats models package in Python. So if you want to start reading about it, you can you can find some information here. And optionally, if you want to read more about generalized linear models and additive models, here you have some information about them. If you want to find more about selection procedures, you can read chapter 6.2 on shrinkage methods. Chapter 7 if you want to know more about moving beyond linearity, so modeling things that are not just a straight line. And again, 2 books on regression if you want to really dive into it. But again, at least go through these 2. And again, these 2 are going to be covered in the regression model, the regression lab, and also this one for logistic regression. But if you want to start reading about it, just go ahead. So this was the lecture for today. It was finite regression. And again, it was about taking the linear model as a mathematical tool and start looking at it from a statistical tool so that we can start making inferences about populations, quantifying sampling error, etc. There should be a lab coming up tomorrow on regression. And I think we're done here. So we have a question. During every lecture, we get a lot of information. Do we need to know everything for the final exam? Well, tricky question. The answer should be yes. You should know everything that you're told during the lecture. But of course, it's also about you figuring out which parts are important and which parts are not. So, as usual, like any other course, I guess. If you're looking for which parts exactly are gonna get into the exam, all of it. The part that is something like this one on generalized additive models. This is just given as pointers so that there's something else. It's not just a linear model that we have seen so far. There are other generalizations, so you do not need to know about this, and that's why they are under optional reading. But in principle, yeah, everything from the lectures. As usual, I'm going to stay here a couple more minutes. If there's any question coming up, I'll just answer. And if not, see you next week.